Okay, so MJ had some questions about 9.4, and in particular, I think she was asking about question 23. Is that the coconut problem? Okay, so they're studying head injuries on some tropical island, and 2.5% of admissions to the hospital were due to falling coconuts. I really hope they're making this problem up, although it seems to actually say this, it's the Journal of Trauma. I think it's kind of funny that that many injuries would be due to falling coconuts, but whatever. All right, if you had 20 patients admitted to the hospital during a certain time period, what's the probability that no more than one of the patients was there because they are struck by falling coconuts? Do not use normal probability for this one. What is that? What's going on in this problem?
People are getting hit
Hit or not hit
yeah.
by coconuts, and we want to know what's the probability it's no more than 1. In other words, the probability that the number is 0 plus the probability that the number is 1, right? All right, and what kind of problem is this? This is clearly a binomial problem, right? There's successes and failures over a series of trials. So this is the binomial probability of 0 out of 20 or 1 out of 20. And each individual event has a certain probability of success. That probability, that little p, was 0.025, right? So this is just a binomial theorem problem. I don't have the binomial theorem memorized right off the top of my head here, but this part of the problem shouldn't be too big of a deal, right? It's just do the binomial probability of, well, let's actually find that thing. Which one are we on here? That was in section 9.3, right? 9.3 is binomial theorem. No, that's normal distribution. Which one's binomial? Where was binomial? Was that actually in the previous chapter? I think so too, yeah.
It was in 8.4, not the one that's 8.4.
8.4?
I think.
Yeah, I think you're right.
Okay.
8.4, yeah, that's the one because it's got Pascal's triangle in it. Okay, so the probability of x successes and n trials is combinations. Here, let's actually write this. So the probability of x out of n is combinations of n comma x times p to the x times 1 minus p to the n minus x. Alright, so we just plug all these numbers in. So like this probability here, the probability of getting 0 people being hit by a coconut was combinations of 20 things taken 0 at a time times probability to the x power 1 minus probability to the 20 minus 0 power. And that's going to be a bunch of tapping on your calculator. Plus, same thing for 1. Combination of 20 things taken 1 at a time plus the probability to the x power plus 1 minus that probability to the 20 minus 1 power. So that's all they're looking for here. It's a bunch of arithmetic. Or like a line on a spreadsheet. But it's not going to be that big of a deal. That's part A. Part B, you know where this is really going on this problem, right? Because section 9.4 is about using the normal distribution to be making approximations to this. So, sorry, I turned the dot to the wrong page here. 9.423. Suppose 2,000 patients were admitted to the hospital during a longer time period. What is the approximate probability that no more than 70 of the patients are there because they were struck by falling coconuts? Can you see immediately how that would be a nightmare to solve this way? Because it would be the probability of 0 people being hit, plus the probability of 1, plus the probability of 2, all the way up to 70. Plus, think of how awful those numbers would be. I mean, there would be things like, n would be 2,000. These numbers raised to like the 2,000th power are going to be really, really tiny or really, really big. I mean, the rounding is going to be a big problem and so on. So this would be a great example of the kind of problem where that normal approximation is going to make a whole lot of sense. Because here's the deal. The number of people being admitted is going to be distributed by the binomial theorem in a way that looks a lot like the normal curve. There is some expected value near the middle here. It happens to be n times p, which is 2,000 times 0.025, 25 per 1,000. I think that's 50. Is that right? Is 22? I think it is. So right around 50 is how many people we're expecting. But we're asking no more than 70. We want this area. This, any place in here, that is, we got 70 or fewer. All right. In order to do that, we need to find the z-score associated with 70. Remember, z is our observation minus the mean divided by the standard deviation. All right. To do that, we better flip back to that 8.4 again. No, is that where it is? What section had that? The mean and expected value of the normal distribution. Ah, there it is. It is page 439. Let me do the math here real quick and make sure I got this right. So it's 2,000 times 0.025. Yeah, that's 50. Okay? And the standard deviation, according to page 439, it's the square root of np1 minus p. Square root of np1 minus p. So this is square root of 2,000 times p, which was this, times 1 minus p. Right, we already know this part is 50. Square root of 50 times 1 minus 0.025. All right, let's see what we got here. 1 minus 0.025 equals this, times 50 equals this, and square root of that thing, oops, I just messed it up. 1 minus 0.025 is that, times 50 is that. So this is the square root of 4875. Square root of 4875 is 6.95. All right, that's the square root of this distribution. I'm sorry, that is the standard deviation of this distribution. It's a measure of how broad the distribution is. So, our z-score is 70 minus 50 divided by 6.95. Well, I hope I'm doing this one right. So, that's 20 divided by that number. 20 divided by 6.95, roughly, is equal to 2.88, roughly. All right, so we are 2.88 standard deviations from the mean. Have you looked at the back of the book what the answer to this problem is?
Yes.
Is it a big number?
No.
It's not?
Close to 1.
It's close to 1.
Yeah.
Yeah, okay, so that's a probability, remember? Yeah, so it's a big probability. Okay, good. All right, so we are at 2.88 standard deviations. Now if we go to page 813 and 814 to find the area under the normal curve, we added z on page 814, find the row that is 2.8, find the column that adds an 8 at the end, and we're at 998. So the probability associated with this z-score, this area underneath here, is 0.998. In other words, if you remember the caption on the curve, that is the area to the left of that value of z. So there is a 0.998 probability that we would have 70 or fewer. Is that the right answer?
Yeah.
In the book. possibly off by a tiny bit, okay? Because I did do a little bit of rounding as I was doing these. So what we did is we found the mean and the standard deviation just based on the information we had in the problem about the sample size and the probabilities. We found that we would expect about 50 people to come into the hospital's emergency room with head traumas associated with coconuts. But we say, but that's going to vary from year to year, from one sample of 2,000 patients to another sample, there will be some variation. The question is, how weird is it to have 70? And what we would find is 99.8% of the time you would have 70 or fewer. In other words, if you had 71 patients, that's a very exotic possibility. It's not very likely that happened just by chance. If 71 people show up with head injuries, it's not very likely that was by chance. Like maybe this year was the coconuts were dropping more people were sitting under the coconut trees or something like that. Why are these people getting hit by coconuts? All right. Let's look at 25. That was another one that you had questions about?
Yeah, I also had 24 part B, but...
Yeah, well, I want to focus. We can talk more about those. I don't want to spend the whole period on these myself. Okay. No, I mean I'm not. I don't want to discourage you from asking about it. I just want to focus on a couple of them.
Right.
All right. 25 is the one about the flu, isn't it? Mm-hmm. Okay. 25 is the one about the flu. So we talked a little bit about this one the other day. This is the flu inoculation one with 80% probability that it'll prevent the flu. The county health offices inoculates 134 people. Find the probability of the following. Exactly 10 people get inoculated that are get inoculated get the flu. All right. So the probability that you are okay, here I'll even write that. The probability that you're okay, that you will not get the flu is 0.8. The sample size is 134. Right off the bat, we could find the mean. How many people of those people are going to be okay? That is n times p, which is 134 times 0.8. And that's 107.2. The standard deviation, so there's some bell curve, right? The probabilities are such that we would expect about 107.2 people to be okay. It could be that just by chance almost everybody's okay. It could be just by chance not very many people are okay. The standard deviation, how broad that distribution is the square root of n times p times 1 minus p. That's the square root of 107.2 times 1 minus 0.8, which is equal to the square root of 21.44, which is equal to 4.63. Now, the way the problem is actually worded, it says exactly 10 people inoculated get the flu. All right. Now, when I hear exactly, one way to do this would be the binomial theorem. To say the probability 10 out of 34, 134, I guess another way to say it would be, how about 124 out of 134? This is how many people are going to be okay, right? We're defining P in terms of how many are okay. All right, so the probability 124 out of the 134 are okay will be combinations, 134 things taken 124 at a time, times that probability, 0.8, raised to the x power, times 1 minus 0.8 raised to the 134 minus 124 power. And that all looks kind of bad, but calculators can do things like that, right? I mean, combination 134 things taken 124 at a time is not going to be a vast number. okay, it'll be big, but it's not going to be like, you know, really, really, really big. And then this will be a very small number, but I mean, this could be done. And this might even be what they wanted you to do for that problem. It does not actually say, don't do this using the binomial theorem, nor does it say, don't do this using the normal approximation. But both would be okay. So this could be done using this binomial right here. It would be a bunch of math, but it could be done. Or we could say, look, if they're saying we're talking about 124 people being okay, what they really mean is between 123 and a half and 124 and a half. We want to know this area minus this area. So that what we get is just that little gap in between. That again would be a z-score thing then. We would need to find the z-score, we'll call this one, let's just call this z above, and we'll call this one z below. Z above would be 124 and a half minus the mean divided by the standard deviation. And z below would be 123 and a half minus the mean divided by the standard deviation. You would have to do the arithmetic to actually find the numbers for z above and z below, and then use the tables on page A14 and actually find that area that's in purple cross-hatching, find that area that's in red cross-hatching, and then subtract the two. And they would be reasonably good approximations to this answer. You can see why they liked this before calculators and before spreadsheets and so on, right? I mean, we can look at this and say, oh, that looks ugly, but 0.8 to the 124th power is just 0.8 raised to 124 equals. I mean, you're not going to like it on your calculator because it's probably written with a negative exponent and all that kind of stuff, but life goes on. Can you imagine before calculators what a nightmare something like this was?
Well, I mean, considering the fact that my calculator won't even calculate 134, the exclamation mark.
No, yeah. No. You definitely don't want to do that.
I did the 0.8 to the 124th and
Yep, yeah. But they didn't like this, right? Because what is this? This one right here. Okay, let's. Oh, I like her problem. Okay, she's talking about this term here, right? Which is going to be 134 factorial over. Is it?
10 factorial.
Over 10 factorial, right? Because it's 134 minus 124, the quantity factorial, right?
Well, and then you still have to have.
And then it has the other one too, doesn't it?
Yeah, 124.
And then it has 124 factorial. Okay. And she said, well, wait a minute, I plugged in my calculator 134 factorial, and your calculator barfed, right? Because it's a bigger number than your calculator can do, right? Right. Because once you have big numbers, if you have a number bigger than about 10 here in one of these factorials, it's never the case that you actually do it. Rather, what is 134 factorial? It's 134 times 133 times 132 times all the way down to 125 times 124 factorial. Well, then those canceled out. So you just have the 134 times 133 times 132. Or you could use any number of websites that are a combination calculator, right? If you Google combinations calculator, you can get that. Or whatever, yeah.
Which I plugged the whole thing in, like all of that, and it's still zeroed on me. So,
Oh, it did?
yeah, I didn't like it.
I'm interested in this. Let's find out the answer. I am intrigued. All that forms up. Let's zoom in a little bit. Let's zoom in a lot. Okay. So, alright, so there's our actual value. And I agree, that first part is kind of hard. Alright, if we actually wanted to do the factorial of 134, it is a giant number. Notice what the number is. It is something roughly 2 times 10 to the 228th power. That is many, 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 many times more than there are atoms in the universe. Okay, that is a very, very large number. Your calculator is not happy with that. Okay? But that is, in fact, that is 134 factorial. Okay? And then, what was another one? We needed 128 factorial. Again, if I just do factorial 124 factorial, it's again a giant number. We also needed factorial 10. This is 10 factorial. But if we actually wanted to do that combinations then of 134 things taken 124 at a time, it would be this number divided by the product of this number and this number, and you get a giant number. I mean, that's a big number. Quadrillions. Okay? Or, over here, I actually just used, you see over here on my function, I just used combin and did it the cheap and easy way. But, how could we have done this without using all that math? Remember how we did it over here where we said, let these cancel out? So you do have 134 times 133 times 132. We could have done it that way too. Right? So let's see, this is going to be equals 134 times 133 times 132 times 131 times 130 times 129 times 128 times 127 times 126. I can even type times 125. It's a big number. And that's going to be divided by that 10 factorial number. And notice we get the same big number again. So there are lots of ways this could be made to work. And you can imagine this is all horrifying before computers and typewriters and calculators and all that stuff, right? Can you imagine the poor, sad grad student whose job it was to figure out 0.8 to the 124th power? Can you imagine how sad that was to do that on paper? Right? No wonder things like this normal approximation sounded great. Right? That was just arithmetic. This is a mess. All right.
You want this one?
I do if you have it done. Do you have it done?
I was kind of confused on 24. But
24? Let's take a brief look at 24. At least talk about it for a minute here. 24. Drug effectiveness. A new drug cures 80% of the patients to whom it is administered. It is given to 25 patients. Find the probabilities that among these patients the following results occurred. A. Exactly 20 are cured. What makes us happy about that problem? I think that one, my first choice would be to do that one using a binomial. Right? We know the probability any given patient is cured is 0.8. We know the sample size is 25. And what is the problem asking? How many are cured? Exactly how many? 20. So we are really talking here about the binomial probability that 20 out of 25 are cured. Well, that's going to be the combination of 25 things taken 20 at a time, 0.8 to the 20th power, 1 minus 0.8 to the 5th power. All right, I think that the arithmetic of that would be a mess, but it could be done. Or we could do it like on a spreadsheet or on your calculator or whatever. Combination of 25 things taken 20 at a time is this. The 0.8 raised to the 20th power is this tiny little number here. And 0.2 raised to the 5th power is this number here. And then we take this one times this one times this one. And this should be that probability. Is that the answer in the back of the book? Oh no, there's 24. It's not in the back of the book. That seems like a fairly high probability. mean, roughly 20% of the time we would get exactly 20 of the people. Hey, numerical literacy kind of thing right here. What do you think about that answer?
I think I messed up.
Well, wait a minute. We gave it to 25 people, and we expect 80% of the time for it to work. What was our expected value then?
Oh, I got close to that.
Yeah. It's 25 times 0.8. What is 25 times 0.8? Where's my phone?
20.
It's 20? In other words, we're at the expected value. This is the one that should have the most. I'm actually not terribly shocked by that number then. All right. All are cured. What would be the way we would do this for all are cured? How about 25 of 20? 5. 25 of 25. 8 to the 25th power. This one to the 0. What are the probability of that? Hey, we can probably just edit that over here. So, combination of 25 things taken 25 at a time. 8 to the 25th power. And 2 to the 0th power. And look at that. Our probability is tiny. Way less than 0.5%. Because we really don't think that's very likely to happen, right? If 80% of the time it works, and you had 25 times where you could fail, it's not very likely you're going to be successful all 25 times. All right. What was... No one is cured. Oh. Zero out of 25. 25 things taken 0 at a time, 0.8 to the 0, 0.5. 25 things taken 0 at a time, 0.8 to the 0th power, 0.2 to the 25th power, rounds to 0. Whoa, 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 that didn't work.
I got like
0.2 to the 25th power.
oh, not that.
That's right. Huh. Google actually rounds that to 0. That's interesting. 0.2 to the 25th power is a really little number. So little that the spreadsheet rounded it. All right. 24, I'm noticing so far we have not done the normal approximation.
So for like letter C, if I put like 0, I guess.
Yeah.
that would be okay.
Yeah. Because it must be damn small.
Because whenever I actually like did, I think I did the Z-score thing. And it
Yeah.
was
Well, hold
not
on. That could
sharp.
be. Hold on. Just out of curiosity. 1 and 0.2 to the 1 power. I'm just curious. I don't know how. I wasn't expecting this to be quite such a big number. Such a small number. Let me just see what's going on here. So look how small. So this is 0.2 to the 9th power, to the 10th power, to the 11th power. Look, after the 14th power, it rounds to 0. All right. So we're way into the... Now, you're thinking this problem didn't have anything to do with the normal approximation, but you could have done all these problems with the normal approximation. But then you hit part D.
I tried doing it with normal approximation and it was not coming out to the answers that we're getting out here, so.
Okay.
So
What would all have cured then? We would have had... All right, let's do that one with the normal approximation. If we're going to do this with the normal approximation, we're going to need to have a z-score associated with these things. Where z-score means x minus mu over sigma. Mu we've already decided was 20, right? 0.8 of... And sigma will be np1 minus p, which will be, that's 20 times 0.2. Square root of 20 times 0.2, just do that real quick here, equals 2. Square root of that is, did I do that right? Yeah, so this is 2. So the standard deviation here is 2. All right, so all of them are cured. All. Z equals, we have secured 25, the mean was 20, the standard deviation was 2. 5 divided by 2 is 2.5. So then we go on page A14, and we look up 2.5. That's a row about 3/4 way down the page, and we get point. Hold on. Yeah. So, yeah, it's 994. Okay, that probability is then 0.994. Now, I'll show you that. Now, what did we have before? When we did it the binomial way, we got like a tiny little number. This is the probability 25 or fewer are being cured. I didn't do this quite right. We needed to have probability 24.5 or more are being cured. That make sense? We want to know the probability 24.5 or more are being cured. So we would do the same numbers again. We're going to get a slightly different z-score. We'll get a slightly different p, but it's still a big P. Let's say it's 993. That is a probability 24 or less. So 24 or more will be 1 minus that tiny number, which will be very, very, very close to what we had before when we did it with the binomial theorem. You see what I did here? Probability, all of them are being cured. All 25 means probability 24.5 or more are being cured.
Okay.
Right?
Okay. I did it where I did like 25.5 and then I did 24.4 and then I subtracted.
Oh, that would
Is
also,
right?
that would be okay. Why would that still work? Because the probability of 25.5, when you did the z-scores, that you got such a vanishingly small number, you were subtracting off a little teensy tiny piece that didn't change anything of the result. Right? I mean, those numbers got to be really, really tiny, right? Yeah. Okay. All right. So these problems we could do both ways. That normal approximation gets better and better the bigger the sample size is. So on the problems where we had 2,000 coconuts falling, we got a lot better answers that were closer than when we did like 25 people got the shot or whatever. All right. All right, before we get too much farther, I do want to cover some new material so that we have stuff, okay? Let me cover some new material here, and then we have a new problem set to do. All right, we're going to continue talking about Markov chains. I liked the Markov chain thing. I'm sorry that I was having an aneurysm or whatever it was on Monday. Too many weird things were happening at the same time, and then I'm getting observed. Anyway, it was a whole weird thing. We're going to be talking about, in section 10.2, a variation on what we've been doing so far. This is going to be called regular Markov chains. And this word regular could be kind of misleading. It doesn't mean regular like this is the normal one. This is regular as in like recurring. It gets into a pattern. Okay? And to understand what's going on with this here, let's go back to our 3 social classes problem again. Like what we were doing on Monday. And we, remember, had 3 different social classes. Group 1 was the people who had no money. Group 3 was the Sir Topham Hat Monopoly Man guy. And Group 2 was sort of the middle. And we built a transition diagram of the probabilities that the next generation of each of those individuals would have moved or transitioned to a different social class. This, as you've seen in the homework, can be used for lots of different kinds of problems and is in fact generally used in like physics or circuit design and computer science more so than necessarily social class type things, but we'll work with this example because it's easy to think about. So this is literally the exact same slide we had before, and we said, you know what, okay, this kind of worked when we had 3 groups, but if we had more states, this would get to be a complicated thing fast. realistically, the transition diagram helps us think about it, but what we really needed was the transition matrix that showed the probabilities each state would transition to a different state. And so, just to review, remember we had a transition matrix, which we labeled last time P. Each row represents a state we're in now, and each column represents the probability we'll move in the next generation or the next iteration to the new state. So, for example, people in group 3 have only a 12% chance that their children will move to group 1. And they have a 52% chance that their children will be in the same social class they were. And all we had to do was raise these matrices to powers in order to get, well, what would the grandchildren's probability matrix be? Excuse me. Now, by raising it to a power, I don't mean like taking to the numbers in here and square them. I mean we got to do matrix multiplication here. What's going on with my phone? Somehow, in the last few minutes, I've gotten like, I don't know what's going on. All right. So no, I mean, it's literally matrix multiplication. I mean, we're going to literally do the things we did back, like at fall break. This times this, plus this times this, plus this times this. We got to go through that whole rigmarole. But matrix multiplication isn't the end of the world, plus you have spreadsheets that can do it, and so on. So we literally have to figure out things like p squared, which is the new transition matrix. We could take the current population, and this is their probabilities. For example, if you're in group 3, your grandchildren have a 19% chance of being in group 1. They have a 34% chance of being in group 3. And again, these are literally the same slides we had before. I just fixed the font problem. But what was... I mean, this was neat. And you guys did this sitting in your 3 groups or whatever and playing with 20 individuals. But what makes this powerful is we can apply it to large populations at the same time. Remember, again, we're just still showing same slides we've shown before, where, like, if we knew that 21% of the population was in group 1, 68% of the population was in group 2, and 11% of the population was in group 3, we could find out what that distribution will be in the future. Like, in the next generation, will there still be 21% of the people in group 1? Will there still be 11% of the people in group 3? And the way you did that was you created this little 1×3 matrix. We called it X naught. I don't know why they chose that symbol. That is just each of these numbers. All we did was X naught times B. So the current distribution times that transition matrix gives us the new distribution. Let me give you a powerful vocabulary word here. A matrix that only has one row has a special name. It's called a vector. I don't like that, but I get it why they have that. Those are called a vector because, I mean, remember when you learned vectors in like trig and pre-calculus and stuff like that? They were like here's some parentheses, and there were number, comma, number, comma, number. It was just sort of an ordered list of numbers. We often interpret them as like the ending point of a vector, like as in an arrow. But after a while, we didn't actually need to be drawing arrows. Just the ordered coordinates of it was enough. That's what this is. It's like a coordinate. It's harder to think how this could be a vector, so we call these things vectors. Okay? It's just a vector in the sense it's an ordered list of numbers. Your book is going to call this like the population vector or the probability vector or something like that. You're going to see this word vector coming up several times in the rest of this lecture. A vector is just a matrix with only one row. So now that we could see, like, if we knew what the population distribution was now, all we did is take this times our transition matrix and we know what the next generation is. And we could see things like, oh, look, we went from 21% of the population being in the first class to being 25%. We went from 68% of the population being in the second to 55%, and so on. And we could do that as many generations as we wanted. It's just that it gets to be a lot of arithmetic. It's easier to do this on a spreadsheet. So let me show you what I did yesterday sitting in my office. I set up that same transition matrix. Here it is right here. This is that same matrix that we've been looking at all along that has the probabilities for class 1, class 2, and class 3 making the transition. And then all I did was I figured out what is p squared, p to the third, etc. So like for example, to get p squared, I made this equal to matrix multiplication of this matrix times this matrix. I'm sorry, no, this matrix times this matrix. I actually did it with named ranges, but I'm that kind of spreadsheet rock star. I'd love to show you how to do that if you want to know how to do that. But anyway, point is, I was able to get p squared. That is the probability distribution, that's the transition matrix for the grandchildren of the current generation. And I could do the same thing for the third generation and the fourth generation. This is p squared times p. P to the fourth is p cubed times p. P to the fifth was p to the fourth times p. Okay, I just keep copying. Once I had this in, it was 3 minutes of work. It wasn't that big of a deal at all. I could have done this hundreds of times. And in fact, when I Googled making sure I was doing this right, it turns out lots of people do these things, like for teaching demonstrations hundreds of times. It seemed a little annoying to keep cutting and pasting the same thing in there hundreds of times. So I went in only as far as 10th generation. But this is the p to the 10th is literally p to the 9th times that p. P to the 9th was literally p to the 8th times that p. I mean, I just kept copying and pasting the same formula. But like I said, I did the whole thing in like 3 minutes. Probably wasn't even that long, to be honest. Alright, so like p to the 10th. This is the probability distribution, the transition matrix for what will 10 generations from the current generation look like. I take my current x naught, how many people are in class 1, class 2, and class 3, I multiply it by this, and I'll get what 10 generations from now we think the distribution will be like. We don't know what any one individual is going to do. We don't know what the 10th grandchildren of this person will be doing, but we don't care about that. We care about what is society. Okay? So we want to know how many people. Are we growing the middle class? Are we growing the bottom class? Are we growing the top class? Whatever. Well, let's start figuring out what will happen. Here's our original distribution. X naught. X naught is our distribution matrix, distribution vector. So 21% of the population was in group 1, 68% of the population was in group 2, 11% of the population was in group 3. And all I did was multiply that by each generation's transition matrix. So for example, this, our current distribution, times p squared will tell us what the grandchildren look like. 27% of the grandchildren will be in group 1, 51% of the grandchildren will be in group 2, and roughly 22% of the population will be in group 3. Or I could do the same thing and find out in 3 generations, or 4 generations, or whatever. Like just for example, after 4 generations, we take the original population, multiply it by the 4th power of the transition matrix, and we get the new distribution. We now know 4 generations in the future that 26% of the population is going to be in group 1, 49% of the population will be in group 2, and 22% of the population will be in group 3. And I can keep going all the way out and down to the 10th generation. I took the 10th generation. I took our original population distribution vector and multiplied it by the 10th power of the transition matrix. And I now have, in 10 generations, what the population will look like. And in that case, 28% of the population will be in group 1, 48% of the population will be in group 2, and 22.5% of the population will be in group 3. And of course in real life this wouldn't work. Because in real life, There's lots of other things that can happen, like changes in tax policy and recessions and all that kind of stuff, right? I mean, this works better for a physical system where the rules aren't changing on us. And we can talk about like the 10th time a photon interacted with that atom. And as it changed electrons from different orbitals or something like that. Or the 10th time we compressed this file. Or the 10th frame where we're trying to keep track of what color the pixel is. And things like that. Okay, physical systems make more sense than people on this sort of problem. All right. Let's actually look what happened to each of the groups with respect to time. I mean, class 1 started off with 21% of the population. And then there's the grandchildren, the next generation, the next generation. By the 5th generation, it was 28%. It's growing. 28% of the population is now in class 1. And in fact, if I just keep scrolling down, here we go, here we go. This is the 10th generation. We get 28.6% of the population has been in group 1. Hey, notice though, we've actually been at about that for several generations. At the 6th generation, we were pretty close to 28.6, pretty close at 7th, pretty close at 8th. See how we kind of hit some sort of equilibrium? After a number of generations, actually the population, we aren't changing the number of people in group 1 very much. That doesn't mean that each individual isn't changing. That doesn't mean that each generation isn't changing. If I'm in group 1, my kids still have some probability the next generation of being in group 2 or some probability of group 3, but we've reached a point where just as many people are leaving group 1 after a generation as joining group 1 coming from group 2 and group 3. We've reached some kind of equilibrium. Class 2. Class 2 started off with 68% of the population, and then became 51%, and then became 49%, and then became 48.9% by the 5th generation, and in fact, if we keep scrolling down, the 6th, the 7th, the 8th, the 9th, the 10th, by the 10th generation, we're 48.9% of the population, and actually, really, since the 6th generation, we've been stuck there. See how we kind of hit some equilibrium here? Doesn't mean that any individual, does not mean that group 2's kids are all stuck at group 2. Some group 2 kids move up to group 3, some group 2 kids move down to group 1, but just as many are moving out of group 2 as are moving into group 2. We've reached an equilibrium. I bet you're shocked to see that that's going to be the case too with group 3. Group 3 started off as 11% of the population. They grew quickly to 22.5% of the population. But at the 10th generation, we're still at about 22.5%. It means that, yeah, lots of group 3 people move to group 1, lots of group 3 people move to group 2, lots of group 2 people move up to group 3, all that kind of stuff. But we've reached an equilibrium. Just as many people are moving out of group 3 as moving into group 3. We have reached some kind of new equilibrium. We started off with some groups of people in different percentages of the population, and after a handful of generations, we kind of migrated, we kind of gravitated towards a new distribution. What if we started with something different? Like we started where our original distribution was 21% of the people were in group 1, 68% of the people were in group 2, and 11% of the people were in group 3. What if we did something different? What if we had 0.1 of the population was in group 1, 80% was in group 2, and 10% was in group 3. So I'll take that original distribution and I'm going to swap it out. And all I did is I just went into the spreadsheet and changed these numbers. Bleep, bloop, bloop, the spreadsheet changes. What happens? I go down to the 10th generation and look at my distribution vector. 28.6% are in group 1, 48.9% are in group 2, 22.5% are in group 3. Does that ring a bell? Those are the same numbers. I started with a very different distribution of the population, but over the course of 10 generations, it gravitated towards the same equilibrium. It didn't matter what I started with time, if that's the transition matrices, it gravitates towards this solution. reach the same equilibrium solution. In fact, no matter what numbers I put in there. If I make it that 100% of the population were group 3, we're all riches, whatever, in a couple generations it looks like this. If I put us all as group 1, the economy was destroyed and we're all poor and we're all eating dog food. In a couple generations it looks like this. And we've got 22% of the population looking rich. For that transition matrix, this is the answer. After a handful of generations, they migrate to being in this distribution. Isn't that weird?
Is that where the V2 equals P comes from?
Yeah, we'll come to that. Yeah, exactly. So we are headed towards an equilibrium solution here, as long as the rules don't change. Remember, one of the key things of a Markov chain is we're saying the transition probabilities aren't going to change. Of course, in the real world they do, right? Tax policies change, things like that, and we start changing how people... But as long as the rules don't change, the distribution will change. That's really unusual. The book uses another example where they talk about 2 dry cleaners. Lisa and Malia both run a dry cleaning business. If I am a customer of Malia's dry cleaner, there's a certain probability next time I'm also going to bring my stuff to Malia. Or there's a probability I'm going to try Lisa instead. Andrew is a customer of Lisa's dry cleaning. There's a certain probability next time he has to get something cleaned, he'll take it to her. Or there's a probability they'll take it to you. Over time, not just me and Andrew, but thousands of people making the same choices, we're going to gravitate to, instead of many generations, we're talking about many times of going to the dry cleaner, to some solution where a certain percentage of the people are going to Malia and a certain percentage of the people are going to Lisa. Right? It doesn't mean that people aren't changing. If I went to Malia this time, I might go to Lisa next time, but just as many people will change from Malia to Lisa as people change from Lisa to Malia. And guess what? Nothing changes that. If the final solution is 50%, if the equilibrium solution is 50% of the people go to Malia and 50% of the people go to Lisa, if currently you have 40% and she has 60%, you like the fact that after time it's going to change, right? You not doing anything special changes it from 40% to 50%. You're crabby about it. You not doing anything wrong changes it from 60% to 50%. For her, it makes no sense to do any special advertising or special deals or something like that unless that changes the odds. Unless it changes the probability somebody's going to switch from her to you, it's just wasting time for her. Because with time, her 60% is going to become 50%. And there's nothing she can do about it without changing the rules. So in this case, we were with the 3 classes. We started with 2 different initial distributions of the classes. And what we found out is it didn't make any difference. Once we got going and had a couple generations with it, it all gravitated towards that same equilibrium solution. Where generation after generation, we ended up with about the same number of people in each of the classes. And in case you hadn't noticed, that's pretty close to what happens in real life, right? As it says in the Bible, the poor will always be with you. Right? You can't change these probabilities without radically changing the probabilities of how likely you are to transition from one group to another. You end up with about the same. Doesn't mean that some people won't move from one class to another. It means as a group, just as many will be moving in as moving out. So what it talks about is the main thing that we do with these Markov chains is making these long-term predictions. Where is this going? What's going to happen 10 generations? In the long run, what's happening to Lisa's and Malia's dry cleaning businesses? In the long run, how many of these pixels are we changing colors on as we compress this video? In the long run, how many of our electrons are in excited states? All right? Long-run predictions is what Markov chains are for, and it isn't always possible. Not every transition matrix, not every Markov chain will reach one of these equilibrium solutions, but some do. In fact, I've only shown you ones so far where it did. Where it did reach 10 generations in the future, we were at some solution. It wouldn't have had to be that way. There are other ways we could have set up that probability distribution, that transition matrix, such that something weird happened. Like one generation everybody's rich, and the next generation everybody's poor, and then the next generation everybody's rich, and then the next generation everybody's poor. We could have set up the transitions that way. But for the transition matrix I gave you, we did reach a solution where there was an equilibrium, where we had a long-range prediction. We could make long-range predictions about what the distribution of the population was going to end up like. The ones where that's possible are the so-called regular transition matrices. And their Markov chains are called regular Markov chains. How do you know, just by looking at the transition matrix, whether or not the matrix is regular? Well, the answer is, if the probability of that P matrix, the transition matrix, if everything is positive. Now, that we're a little bit loopy about that. I don't like the way they said that. It isn't like any of those probabilities can be negative. But what they mean by that is there's no zeros. But here's the deal. It doesn't necessarily mean P has no zeros in it. It means some power of P has no zeros in it. So, like, if you can get it so that maybe P has zeros in it, but P squared doesn't, or P cubed doesn't, or P to the fourth power doesn't, then it's a regular Markov chain. So a regular transition matrix or a regular Markov chain is one where either P doesn't have any zeros in it, or some power of P doesn't have any zeros in it. But as long as that's the case, then it's a regular Markov chain, and you will have the ability, your future, as you raise these to more and more powers, will always get more and more, will always gravitate towards some equilibrium solution. Now, it took longer to review today than I meant, to go over those problems. I want you to look at example 1 in the book on your own time. It has the example of another one of these. I think it's the dry cleaning one or something like that. I just wanted so that you have some of the vocabulary that you're going to need on the homework set. So remember, we had these two very different initial populations. Here's where I had 21% in group 1, here's where I had 10% in group 1, and so on. And again, just to throw the vocabulary around, your book is calling those vectors. Originally it was calling them population vectors, and then it switched to the word probability vectors. I get why they call it probability vectors. They're saying there's a 21% probability you're in group 1, you're a 68% probability you're in group 2, whatever. Okay, whatever, however they want to call it. Yeah.
Do we have this class?
We do.
We have this class Friday?
Yep.
I did not know that. I won't be here.
You're not here on Friday?
No.
Okay.
Yeah, but we did have this Friday.
Okay. Remember how we ended up with the same result after 10 generations? That was called the equilibrium vector, or the fixed vector. That's another way to put it. And I already have introduced that term to you, but the book wants you to see here that as long as that transition matrix P was regular, then there's always going to be some equilibrium vector, and we're always going to be headed to it. In other words, a regular transition matrix will drive the system over a period of generations toward that equilibrium. Whether that's the distribution of different socioeconomic classes getting driven toward some sort of equilibrium that lasts over generations, or whether that's how many electrons or how many atoms are ionized in this gas as we shine this beam of photons through it, or whatever. Turns out, whatever you start off with doesn't really matter. Over a period of time, over a period of transitions, over a period of generations, whatever, you'll head toward that equilibrium vector regardless of what you started for. Now, your book very confusingly calls that equilibrium vector big V. That is where you head over a period of generations or a period of transitions. Whether that's representing class 1, class 2, class 3, or that's representing how many people go to Malia's dry cleaner versus Lisa's dry cleaner. It's big V. Why the hell they did that, I have no idea, considering that starting probability vector, what you started with, the original generation, whether that is how many people are in each of the economic classes, or how many people go to each dry cleaner, they they use the symbol little v. I could kick their butts. Because those two letters look alike in the small and the big, minuscule and the capital. But it is true then that wherever you started, times p to some power, it's going to be approaching that new equilibrium. This is what we've been saying all along. We started with some population, and we said, what about the nth generation, the second generation, the third generation, the fourth generation? And what we see is it gets closer and closer to that equilibrium. That's what they were doing here with V, 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 P, V, all that kind of stuff that's in the book. So this is just a fancy mathematical way of saying what I did on the spreadsheet there. That after each generation, generation n, the population is the original population times p to the n power, and it's getting closer and closer to that equilibrium vector. And you might wonder then, do we need to actually do all that matrix stuff? Could we have found that equilibrium vector some other way? The answer is yes. Yeah. You do, but I'm going to probably send it to you as an assignment or something instead, okay? Because I can get it, the word like down to like 3 minutes. I want to hit where this slide is with the final part of this. There is a way to do this, to actually have found out what is the equilibrium state. What will be the final breakdown of the customers of Malia's dry cleaner versus Lisa's? What is the final? And it's a bunch of arithmetic. You effectively get to where you have a system of equations. You don't do this just yet on the assignment, but you can get to the point where there is a system of equations. What is the population that's in group 1, group 2, and group 3, and so on, and you can actually solve this as a system of equations the way we did in literally chapter 1, I believe, of the book. But we're not ready for that yet. But these regular Markov chains have certain properties, all of which we've talked about today. As n gets bigger and bigger, the product of our original population times p to the nth power approaches the equilibrium vector. The population vector, that equilibrium vector does have this property, v times the transition matrix equals v. In other words, each time you take that equilibrium vector and you say, what is its transition, it just goes back to where it was before. You've reached equilibrium. And you could actually find that using that as a system of equations. And I also wanted to show that actually one of the ways you could have found it too is the powers p to the n get closer and closer to that actual matrix. But I won't show you that right now. Oh, I'll show it to you, but anyway, it's not so important. All right. Here's the deal. Here's the assignment. On page 468, 1 through 8, 25, 27, and 25, 28, 29. Now, if I remember right, 1 or 2 of these is about what I just sort of breezed through right at that very last minute of saying, here's how you could have solved for v without having done all the generations. What I'd like to see is for you guys to have taken a stab at that by Friday. Whether you did that, I want to solve for v by just making a spreadsheet and doing a couple generations and see if I can get to v. Or whether you want to look through the book, it's not that hard. It's just a Gauss-Jordan elimination thing. To act, well, yeah, remember you had ulcers about that. And actually try to do it. And the book explains it. It takes like a paragraph. It's not that big of a deal. I want you to at least have taken a stab at solving that problem. Okay? Where it says what will the equilibrium be? All right. We're not leaving the room. We have to have they're taking a test in our classroom today. They're doing the NWEAs or something. So just stay here, okay? And I think that's it for today. All right?
Do you have the homework for this?
What?
Will be here this class.
I don't have it ready yet. Okay. I'll send it to you.
I just don't think I'll be able to get it done because I'm going out of town for my birthday this weekend. I didn't think we have this class.
Okay. I can send that to you. Okay? All right. All right, we're good. Yes, if you have the homework, please can I have that? And
For both of them?
what?
For both?
Why don't we make? Because I know there were people who were scribbling. Do you want a little bit more time on that assignment?
The last one.
I'd rather just turn it in.
You'd rather just turn it in and move on with your lives?
Yeah.
Yeah, me too. If you got it, if you want to turn it in on Friday, you can. If you have something you want to finish out or something like that. We're kind of in a little bit of a mess. I realize that we've had 2 days in a row where we've run a little long. Okay?
It's not going to get done. I don't know how much time, so.
You won't learn.
if you want it, why don't you give me what you have, and I will get started now. Okay. All right.
It's not essentially the most that we just talked about.
All right. I need to go and yell at.
Useful? Yeah, this is actually like I can work with this. It's not a well. It's
Let me
just
go
whatever
yell at,
you can
um,
work. Yes. I pinky promise.
I know Rhiannon's just gonna be like, you know.
Hopefully, at least one of your favorite friends. Wow. Okay. Yeah, you are.
I was like running so late. We had to be car, and my English was completely ice all over. And my dad was really doing this spray stuff. I never used it, but it worked great. And I didn't have enough time because now I have to do it. I didn't have time at once. I'm like sitting in my car driving to using my brand in like 60 years. It's just great. I don't know exactly. Well, Alex just starts cussing out the world.
It's okay if you post that on YouTube and I just say fuck like 5 times.
Oh, okay.
You know, he really doesn't care. He really doesn't care.
Ooh, I get a blue chair. Okay.
I'm so mad. I can't find my leggings.
These are the only ones that I have that don't have holes in them, and you can see right through them. Watch.
I can see it before you even.
Yeah. So then I didn't know it's like.
No, you don't have to, but like literally you stood up and I
I
saw.
know. Meh. I didn't feel like wearing jeans. I'm trying to wear jeans every day.
I was gonna buy some leggings from Black Friday. Anyway, so I bought brushes and please stop.
I just hit my head so hard. I meant to make it a joke and like
It actually hurt.
I didn't realize the wall was this close. Okay, time to chill out. Time for class. Where is everybody? Why someone told me to come in here?
They're probably out in the commons or
Confused.
out vaping in the parking lot.
You think I can put my feet up here?
I wanted to get fit before but my engine was off. I needed to put some coolant in there.
Tell me why. Bernard got so mad at me. He goes, just don't talk to me ever, Alex. And I was like, okay.
Okay.
And then I texted him for 3 hours later, because he's like, I just can't tie. He was being so mean. My feelings were so hurt. And I texted him like 3 hours later.
So he added me back on Facebook.
I was like, so have you had enough time yet? He said, what? I said, have you had enough time yet? And he was like, why? I said, hungry. He said, no. I was like, oh. Okay. Chicken nuggets. Just kidding. I accidentally threw away my tea. I forgot it was full, and I threw it away.
What?
You know how I got green tea? So I accidentally threw it away.
How
Just
did it
like,
accidentally go?
because for some reason my brain saw a trash can and it was like I had to do it. I don't know why. But I couldn't stop it.
Message back. Why?
No.
No.
No, Malia, quit being a psycho.
It's not psycho.
It's
It's
just
just
you
heavy.
are.
It's just heavy.
Chicken nugget. Ew, arms. Chicken
Man,
nugget.
this girl I work with, we were on a Snapchat pictures yesterday, and it was so because she's at the, you know, the one that makes you look really old. She has, oh, this one makes me look look so hideously old. I go, I'm pretty sure that's
Hideously old.
Yeah, I was like, I'm pretty sure that's the point. And she goes, oh.
My butt is cold. It is because it's Maria, don't do that. That's why my butt is so cold. Oh my god, don't do that again. That hurts.
He's like, I like to see.
Whatever on the system is last. Like last.
No.
Other than the freezes.
Just a minute. I'll let Siri. All right, let me just grab a few things here. So.